Okay, welcome to Chapter 5 of Collaborative Statistics, uh, Continuous Random Variables. Now, this is different from discrete random variables in a couple of ways. First off, we're measured and not counted. So, remember last time we had one thing you could have if we looked at 0 through 5. We had 0, 1, 2, 3, 4, 5. Well, in this case, we can have anything in between those. All right, so it doesn't have to. They can be decimal points or fractions. Yes, we could have whole numbers, but we're looking. There's a complete range. So we're looking at a graph now. We're looking at the area under a curve, and the area under the curve is always 1. Because we're looking at probability, so that helps us. And we're going to take little pieces of that and find out how big are these little pieces going to be. Now, what we have to do is we have to find ranges. Okay, we're going to look at, what's the probability of this going to be less than. We're never going to find what is the probability of something equal to this. Well, we could, but it almost never happens. We look at the ranges of intervals, from less than 2, between 6 and 13. What's the average IQ scores between, what percent of people have an IQ scores between 80 and 120. So we're always going to look at ranges of stuff, and that those ranges are going to give us the probability distributions are going to be in areas. Okay, so that's the big difference between these two things. So we still have PDF, which is the probability density function. Okay, and we're going to look at 2 common ones this time, and then we're going to look at some more next chapter. So a special one next chapter. But in this chapter, they look at the uniform distribution, which says that everything is exactly the same. They have all the exact same chance, and it becomes a rectangle. And the exponential distribution, which you won't see exponential until trigonometry, but it does come in here. It's part of decay, so they just want you to come across it. And because we're going to use these two things again in chapter 7, that's the only reason I'm talking about them now. Because they want you to see how that other distributions that aren't normal can become normal when we keep taking the averages. So that's why they want you to use these. That's why we want to go over them quickly. So the uniform distribution, as it said, makes a rectangle. So here we're looking at the probability that x is between 3 and 6, and something has an even distribution between numbers 2 and 10. Okay, I don't know what you could make that would get a probability distribution between 2 and 10, but that's what it is. And so there's a height here, okay, and each thing has an equal amount chance of happening. The graph writing for it is x is uniform. We use this little tilde. Is described as uniform with a and b. Okay, so this is our lower bound, this is our upper bound. The probability of each thing happening is 1 over b minus a. So in this case, we'd have 10 minus 2, which would be 8. So the probability would be 1/8. Alright. We find our mean, our expected value, by we take the average of the two. So a plus b over 2. So 2 plus 10 is 12, divided by 2 is 6. So this is our mean, is 6. And our standard deviation is just this formula, the square root of b minus a squared. So 10 minus 2 is 8 squared to be 64, divided by 12. I get 64 over 12. I can reduce that down to what, like 8/3. So I have the square root of 8/3 would be the standard deviation of this. So that's how we go about doing these. Alright, this is the thing we're going to look at for this chapter. You don't need to know much more about it than that, but like I said, every probability, everything has the same exact chance of occurring. That's the big thing about this. That's why it makes a rectangle. The next one we're going to look at is so to calculate, the area to the left, or the probability that a value is less than something, we just take the base times the height. Okay, we find where this is. Okay, 6. This goes from 2 to 6. Alright, that's our base. So we have a length of 1, 2, 3, 4 times our height. And our height is going to be this function, 1 over b minus a. So we have 4 over 1/8. So that would be half of the thing. And then here we had 1 over 1/8. So 1 times 1/8. I have 1/8. So this is 1/8 of the probability is going to be less than 3. 50% that it's going to be less than 6. Area to the right is the same thing. We take our base and we get our height. So again, we're just going to subtract off where those things are and multiply by that frequency distribution. To find an area, we just take the, that should be a minus. Base times height. We have d minus c over times height. So again, we take 6 minus 3 is 3 times our height. Okay, we're just getting an area of a square or area of a rectangle. It's just, remember, base times height. So we have to find how long this is, looking at our number line, and how high this is from our function. Okay. Now the exponential is another one that we have. This, again, like I said, this is something that you don't see, but what it usually has to do with is either exponential growth or exponential decay. And in these we're going to be looking at exponential decay, okay, where things start to get smaller as they go along, as time goes along. So it could be the half-life of uranium, the population of a population of a bacteria, but we're finding how small it goes. So we're taking the largest piece and going backwards. So, and so this is written as x follows the exponential of m, where m is our decay rate. So how as fast is it going down? Okay. And then they are going to give us this value. Okay, they have to tell us how fast it's decaying. Then we get our function is m, our decay rate, times the this is about, actually this letter e is actually a number. It's 2.718 something. It's just like pi. It's a completely irrational number. Raised to the negative m times x. So that's what this is happening here. And m is equal to 1 over the mu. Okay, so sometimes they will give us the average. All right, they'll give us mu. We have to find m. Sometimes they'll give us m, and we have to find mu. So they'll go back and forth. So if m is equal to 1 over mu, we take these, we flip them, cross multiply and divide. Mu is equal to 1 over m. So it just depends on which one they're going to give us. And the standard deviation and mean and expected value are exactly the same. So that's one nice thing. And here, this is a value. This is this thing from 0 to infinity of 1. I can't even read it now. These values factorial. It keeps going. This becomes 2.718. Is basically what happens. So that's what this value is equal to. And like I said, it keeps going all the way. And one of the things that your book says is that it's used in project reliability. Yes, because they assume that it's going to have a 4-year. The product's going to be good for 4 years. So as it goes further along, they're going to have more and more of them. Decreasing. In the short term, they'll have less of them. So it's going to keep going.
Oh, okay, yeah.
Yeah, that's how they work.
Okay.
And to calculate, here's our formulas. We're going to use 1 minus this e constant raised to the negative m over x. So that's to the left. To the right, it's just e to the negative m x. Okay, so that's how we find our areas. Okay, when we want to find between, we just subtract the two. Okay, we want to find between is c is less than d. We end up turning them around. We have e of negative m to the c minus e of negative m to the d. As you look here, here's our this number is going to be higher than that number. So that's why we're subtracting them. This one first. And if they ever ask for a percentile, this ln means the natural log. That's the opposite of raising something to the exponent of e. And we take our value, so we have the area to the right, which is they're going to give us, over negative m. So this here would give us a percentile in k. Again, I don't see you using it all that much in that case, but I think that may be one homework problem, so that's why it's been thrown in there. But this is the big thing. We have this graph that's going down, and we're going to be again trying to find the areas by finding the area of the pieces and subtracting them. Now, the reason it's important is because we're going to be doing that for the normal distribution, which is the next chapter. So they want you to get used to some of these before we start looking at a table of a specific curve. Okay? So this is chapter 5. I will gladly go over a whole bunch of stuff because there's lots that is new in this one, especially the exponential function. But I will see you in class on Saturday.